Welcome to Quantum Curious, and in today's video, I'm going to discuss more physical picture of squeeze state of light. So in the previous lecture, we discussed what are squeeze states and how can we generate them and how they are different from other field of light. And we also saw that how can we write a squeezed vacuum state in Fock basis and coherent states. So this is the outline of today's lecture. First, uh, the we will discuss some review of squeeze state of light, what are squeeze states, and uh, how can we write them in terms of or a superposition of work basis and coherent basis. And then I will try to give some calculation of the expectation values of field operators for the squeezed vacuum state. And these values will be handful in order to show the fluctuations in the quadratures. And we will see that the fluctuations of one quadrature will be squeezed, will be minimized at the expense of the increase of fluctuation in the other quadrature. And then I will discuss the probability distribution associated with the squeeze state of light. So we know that we can build upon or build on a probability distribution uh, by the detection of photons or incoming photons. So we will see that how it is different from other state of light or how it is similar to other states of light. And then I will discuss a way in uh, experiments that through which we can generate a squeezed vacuum state. And we usually in experiments or in laboratories use a nonlinear medium to generate squeezed states. So let's move on to the introduction of today's lecture. So we saw that how can we write the squeezed vacuum state in terms of Fock basis and coherent basis. So this is the expression in terms of a Fock basis. So we can see that the given squeezed vacuum state is the superposition of Fock basis, and these are even Fock basis. So we can see that the squeezed vacuum state is related to two photon processes. And we have two parameters on which the squeezed vacuum state or the weight of the squeezed vacuum state is depending. That is the theta and R. R is a squeezing parameter and its value tells us that how much squeezing we have. And theta is the phase and it tells us in which quadrature we have squeezing. So this picture is very useful to see the even structure in photons for squeezed vacuum states. And we can also write squeezed vacuum state in terms of coherent basis. And this is a very useful form in order to do calculation in phase space. So we have weight associated with that uh, distribution, and this is the Gaussian weight. So this form is very useful in order to do calculations like the calculation of Wigner function. So both the states have their own equal merits. So let's move on to the calculation of the expectation values of field operators. So we know that we can generate a squeezed coherent state using two operations alternatively. Either we can do displacement first or and then squeezing, or we can do squeezing first and then displacing the given resultant state. So both the ways are equivalent and both uh, both give us the squeezed coherent state. So let's move on to some mathematical preliminaries. So we know that displacement operation on the annihilation equation operator just displaces the resulting uh, or just displaces the original operators. So this is the mathematical result for displacement of operation of annihilation equation operators. Sorry. And then we have squeezing operator or squeezing operations on the annihilation and equation operator. So we can derive it using some BCH formula. So I will not going to discuss the details of this calculation, but it can be done very easily. And in the calculations in upcoming slides, I will try to minimize the use of trigonometric functions. So I will use mu and nu to denote these trigonometric expressions. So let's find the expectation value of annihilation operator. So we know that we can write the expectation value as this, as the sandwich between two states. And then we can open up these two states in terms of the displacement and squeezing operations. So we can do these operations and we get this. So this here is some kind of mistake. There should be S and then D. So applying squeezing operation, we have to have this kind of expression after this. And there should be D, sorry, a lot of mistakes. So after applying squeezing operations, then we have to apply displacement operation on each field operator, that is the annihilation equation operator. And this is going to add a classical displacement for each field operator. And then we have this. So we know that if the annihilation operator will act on a vacuum state, it is going to annihilate it. It is going to destroy or annihilate it completely. So these kind of terms will be cancelled out. And we know that if the Cohesion operator is going to act on vacuum state, it is going to have a state that it's one photon or an excited state, but the inner product of both the state is going to be zero because they are going to be orthogonal. So these kind of terms are also going to be zero. So after some calculation, we can derive this result quite easily. So this is the expectation value of Cohesion operator. Similarly, using these kind of steps, we can write expectation value of Cohesion operator. This is for annihilation operator. This is for Cohesion operator. So both the values are same, but here we have a conjugation, a complex conjugation. Then there is an interesting property or expectation value, that is the average photon number. And it is interesting because we can measure it in experiments. So in order to calculate the expectation value of photon number operator or number operator, we are going to introduce a fluctuation operator. So we know that this expectation value is going to be alpha s, and we can write our cohesion operator or annihilation operator as this. That is addition of fluctuation operator plus displacement. Then we know that photon numbers operator is in that form, that is the creation operator and the annihilation operator. So we can use this form here below. and we're going to have this. So after doing some calculation in squeezed coherent state, we are going to have this operation, this expression. So we have to calculate this uh, expectation value for the fluctuation operator. So doing this, we are going to have this. So the initial, so the photon number expectation value is going to be this, as it depends upon the displacement and squeezing parameter. And then we can calculate the expectation value for second order moments, statistical moments, and these are going to be this. So we know that normally ordered variance of quadratures is going to be this, and we have derived it earlier in our lectures. So putting the given values of uh, required expectation values in this expression, we are going to have this expression. And making this assumption, we are going to have this. So after having this expression, we have to expand these in exponentials. And after some simple calculation, we are going to have this result. So we can see that uh, the quadrature of E1, denoted as E1, is going to be squeezed. On the other hand, doing similar calculation with the variance of the quadrature of E2, we're going to have uh, greater variance in here. So here should be a greater sign. So we could see that the product of these two variances is going to be uh, it's going to it's going to have minimum uncertainty. That is the hallmark of the coherent states, but individual variances are quite different. So one variance is greater than greater than zero, sorry, and the other variance is smaller than zero, and it has been squeezed uh, due to the squeezed nature of light. So we could see that using these calculations, we can show that the squeezing in one quadrature, and uh, in order to compensate and in order to saturate the uncertainty principle, the other uh, uh, the quadratures in the fluctuations in other quadrature is going to be decreased. So let's move on to the probability distribution associated with the uh, squeezed vacuum state. So we know that by projecting the given squeezed vacuum state a onto a state with even photon number, we're going to have this expression. And we know that we have no expression of squeezed vacuum state in terms of odd number of photons. So this probability distribution is going to be zero. So we could see that from our previous calculation that the average photon number of for squeezed vacuum or squeezed coherent state is this. So for squeezed vacuum state, this factor is going to be zero. Then we have squeezed that we have photon number for squeezed vacuum state as this. So manipulating this expression, we are going to have this. So it is kind of like a thermal distribution with this extra term. So we could see that this extra term is going to play a role, a crucial role in our interpretation of this distribution and how it will differ from the distribution of thermal state. So this is the plot of probability distribution against photon number, and it has been plotted using average photon number for each state. So we could see that the shaded region denotes or represents the distribution of thermal state as it tails down to zero or nearly zero as the photon number is increasing. But we could see that in the bar representing the distribution of squeeze state, the probability distribution of squeezed vacuum state, it is showing to a kind of an oscillatory relation or oscillatory representation. So for even photon number, uh, it is showing a peak-like structure, but we know that for odd number of photons, there is going to be zero distribution. So that is why there are consecutive gaps between the peaks. So there is a difference between these two distributions due to these expression and this weight. So this weight is going to be zero as we are going to have more photon pairs. So as we are increasing the photon number, we have to form more photon pairs, sorry, because we know that squeezed vacuum state only exists in photon pairs. So the probability of having more photon pairs is going to be very low for more photons in particular state. So that's why the distribution is tailing as we are increasing the photon number. So let's talk about the process through which we can generate squeeze state. So there are multiple uh, processes through which we can generate a squeeze state. So there are degenerate processes and non-degenerate processes. So in degenerate processes, we have to pump the nonlinear medium with a strong classical beam. Then the resulting beam will going to have only one mode for the degenerate processes, uh, and uh, and each mode would have idler beam and a signal beam, and the the field that is coming from the nonlinear medium is going to be squeezed state. But for the non-degenerate processes, there is going to be two modes, and each mode uh, and one mode represents the idler mode, and the other mode represents the signal mode. So individually, individually the modes is going to be uh, chaotic and thermal like states, but when we analyze them together, their quadratures show some kind of squeezing, and this two mode state is going to be squeezed in quadratures. Uh, so this is the difference between two processes. So here we are going to discuss a degenerate parametric amplifier. So the Hamiltonian describing this process is going to be this, and it is a two photon process. That is why we have the squared field operators. So we have to first derive the Heisenberg equation for the field operators. That is going to be this. And the solution of these field operators is going to be this. So we could see that it depends upon the chi, and it shows the non-linearity of the crystal that we are using for the generation of squeeze state. But in terms of the quadratures, we can write our differential equation as this. So solving these equations, similarly, we can see that the resulting our field of quadratures depends upon the time and the nonlinearity of the given crystal. And the variances also depends upon the nonlinearity of the crystal and time. So at time is equal to 0, the quadratures are going to have uh, equal fluctuations, just like a vacuum state or a coherent state. But as the time passes, the fluctuations in one quadrature is going to be decrease and at the expense of the increase in the fluctuation of the other quadratures. So that's how we can generate squeeze state. So that is for all today. That is all for today. So if you like this lecture, kindly subscribe to the channel, and uh, if you have any kind of suggestion related to improvement of my lectures, uh, do comment below. Thank you.